Alrighty, so we're going to look at vertical circles today. We've seen the video with the car. I can post that up to Schoology as well if you want to watch that again at home or something or other. What we've got here is the. Have you got that rubber stopper? What we've got here is like a rubber stopper on a string, and as it goes around, right? Everybody sort of knows that as you sort of go in a vertical circle, there is some speed, just like you saw in the video, right? If I go too slow, what happens?
You don't go.
It just crashes, right? And obviously, a rubber stopper is not a big deal, but if you're driving a car in a loop-de-loop, that's a problem, right? And the faster I go, well, then the more tension there is in the string, right? Is there, in this vertical circle, is there more tension, say, on the down, you think, Jory? Why do you say on the down there's more tension?
Gravity.
Gravity's pulling it down?
Yeah.
Isn't gravity pulling down at the top, too?
Yeah. There's more force going on.
But it's pulling, if it pulls down at the top of the string, it doesn't be
Like if I just go like that, there's no tension at all, right? Okay. So what do you think? I got two vectors here. What do you think the blue and the red vectors represent in that little graphic there?
Blue is your mass, and the red is your tension.
Are you saying the red is the tension zone? Okay, because,
It's more at the bottom.
and not only that, but the red also always points which way?
Towards the middle.
Towards the center. And the blue is pointing?
Outwards. Oh,
Tangent.
No, look at the blue arrowhead.
You can't see.
We can't see it?
Tangent.
It's pointing down all the time.
Oh.
It's always pointing down. So like you said, it's like the gravity, right? Okay, that's good. Okay. Oh, we don't need to.
No, it would be the weight.
Okay, so consider a ball moving in a circular path as shown. What happens to the speed of the ball?
As shown.
Well, it was there, right? What, does the speed remain the same all the time? Steph, put the phone away.
Yes.
Does the speed remain the same all the time? Notice I said speed.
No.
Yeah.
When is?
Yeah.
Yeah?
Or no.
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 Yeah?
If it does full circle, I think.
Does the? Oh, yes, the velocity changes because of the direction, right? But what about the speed? I said speed on purpose. Like
You're changing it right now.
it looks like it, right? Like when I go like this.
Say no slower, faster.
But what if I go faster? Put that phone away, Steph.
It's just not as easily visible.
But it's still happening, right? And it makes sense because on the way up, it's going to be doing what? Slowing down because of gravity. And on the way down, it's going to be speeding up because of gravity. Exactly. So it's not technically UCM.
Is that only on
What does UCM stand for?
Uniform circular motion. Okay?
Is that
That's
only
if you're going
on
this way.
Yeah, like uniform would be horizontal, right? Do you remember there was one or two people that I said when we did the rubber stopper one, I think it was your group, Abby, you were sort of sideways a little bit, and I said you got to make sure that it's as horizontal as possible because if you do this, it's not very uniform. Okay, that was the reason for that. Okay.
That's fun. Let's do that loud again.
Yeah. So what happens to the speed of the ball? It changes, slows down on the way up, speeds up on the way down. What about the tension in the string? Greater at the bottom, less at the top. Now I think, yeah, I don't know. That's that video that I just showed you. Okay, so what I'd like you to do is I'd like you to draw that little picture.
No, watch that video.
Okay. Oh, here we go.
No, I do that.
All right, so because of gravity, the speed of the ball is not uniform. So not just the velocity, but the speed of the ball is not uniform, right? And in fact, we've got V max at the bottom. We've got V min at the top. Okay? And why is that? Well, the ball accelerates on the downward path. So it's accelerating, speeding up when it's moving down here. And of course, it's slowing down on the upwards path, like so, right? Speed is at a minimum at the top and a maximum at the bottom. That sort of makes intuitive sense, does it not?
Yeah.
Yeah, I think so. The guy in the car, now he said that he had to enter that loop-de-loop at 30, it was 36, wasn't it? Was he going 36 at the top?
No.
He wasn't maintaining that 36, was he? No. He would have to, how fast was he going at the top? Could we
Probably
tell?
half.
Yeah, I don't know. Yeah.
So would he be going 36 again?
He should, although I mean he's got there's certainly some friction and some air resistance going on, right? And he's got his foot on the gas. I mean, he could go.
Accelerate.
He could
Yeah,
accelerate.
probably gassed it with that many G's on him, like not 50.
It would be easy enough to do, wouldn't it? Right?
It looked like it was a standard.
What if you put it in coast?
Yeah. I don't know. I mean, ideally would be get it up to exactly 36, hit the cruise, and
I thought you couldn't set cruise unless it was over 60.
I don't know, maybe.
36 miles an hour.
That's what he
Oh, yeah,
said.
good. Too bad they didn't have a little power on the speed.
Yeah,
See the-
that's right. See the change in the speed. I'm sure it did change. It looked to me like he was actually just off the track at the top, wasn't he?
Yeah. Well, he also bottomed out when you see the engine.
Yeah.
Yeah.
Yeah. Yeah. Okay, so at the top.
We didn't explain the F1S.
Oh, okay. Well, let's go back here then. So I've got weight force down, right? I'm going to, FS1 is string force or tension. It's really just the tension. Okay? Tension in the string, right? Now the tension is always towards the center.
You can't use T period.
Yeah, I know. That's why I went FS1.
Okay, that's FS1.
Yeah, FS1, tension. Okay, so at the
How
top,
many letters?
I know. At the top, the centripetal force is string force 1 plus the weight force, right? And they're both in the same direction. So the centripetal force is made up of, is the string pulling the rubber stopper down at the top?
Yeah.
What? Actually, this answer is depends. Because if I'm going fast, is the string pulling the rubber stopper at the bottom?
Yeah.
Absolutely, right? But if I'm going slower, then there's some magical speed where the tension in the string is what? Zero, but it just holds onto that circular path because of gravity. Right? So the centripetal force at the top is the string force, the tension, plus the weight force. Now, centripetal force is mv squared over r, right?
Is this all changing?
Yeah. Centripetal force is mv squared over r, and it's a special v. It's in fact v min, right? It's the minimum speed, the slowest that it goes to the top. So I've got mv min squared over r is equal to the string force plus the weight force. I'm deriving a formula, by the way. Yeah, yeah. Not drinking though, so we're okay. What about at the bottom? At the bottom, and don't get all hung up on positive and negative here, okay? Because I know that sometimes trips people up a bit. The centripetal force is made up of the string force minus the weight force. They're opposite directions because the weight force is down, which means the centripetal force, mv squared over r, that v is max, so it's mv max squared over r is equal to the string force 2, the tension at the bottom, minus the weight force. Does the weight force change?
Sure.
The weight force?
No.
Weight force stays the same.
Sure.
Weight force stays the same. Now, do you think it matters whether or not, like the guy in the car, was that a Volvo or a Yugo or something like that? It was a little tiny little car, right? Was it yours? Could he have done it in, say, like a Cadillac?
I think it was
Would the speed, does the mass of the car matter, is what I'm asking.
Yeah. Yeah.
Here the car was going fast.
Hey? You think so?
And when you make it up there,
Okay. Now, I'm hoping you all agree Vmax is bigger than Vmin by definition. Yeah, the speed component, right? The speed component. Which means that the tension at the bottom, FS2 must be greater than FS1. Tension in the string is greater at the bottom. This implies that there's some velocity below which the ball will not move in a circular path. The string will slacken at the ball's highest point, and as we saw in the car video, yeah, you crash or you don't, right? This isn't near as exciting a video as the other one. So can also happen if a car did not have enough speed to make the loop, to use a technical term.
LU?
Yeah. Now this minimum value is when the string force is equal to 0, right? At this time, the ball just makes it around the circle. In other words, I can't get that to play. When the string force is 0, when the tension is 0, gravity is supplying the centripetal force. Gravity supplying the centripetal force.
That in the top of the loop?
Yeah.
What was I looking at?
It's on its way around. So at the top, now this is what you really need, right? This is what you really need. The centripetal force 1 at the top is equal to the string force plus the wave force, but the tension is equal to 0, so I put a 0 in there for my tension. And I got mv min squared over r is equal to mg, and guess what happens? Guess what happens?
Equals 0. Cancel the stuff.
The minimum speed required is when the tension in the string is 0, right?
What's R?
R is the radius. R is the radius. So the tension is 0, which means my centripetal force is all gravity. So the m on both sides cancels, and you get v min squared over r is equal to g, or v min, and that should probably...
So FC1 equals mv squared min over r? Just that part?
Yeah.
Okay. And so you're putting the 0 in?
I'm putting the 0 in for the tension, right?
That's 1.
Yep. 0 in for the tension. So in other words, the minimum speed required to maintain the circular motion is equal to the square root of r times g, where r is the radius, g is 9.8, square root means square root. Is the mass in there? I can take 4 rubber stoppers and it would be exactly the same speed. I could take 100 rubber stoppers, it would be exactly the same speed.
Why?
That's a minimum value.
V min, yeah.
At the top?
Why?
But yeah, at the top, you're right.
It would change.
It would change. It would be the minimum speed, right? At the top.
Why?
I just proved it, that's why.
Why?
Because the mass cancels both sides.
Yeah, I know it counts, but that doesn't.
Now, is that true for the car?
It's not on a string.
Not on a string, you're right, George. So here's a good question then. What supplies the force that,
Wouldn't there be more friction on the car because it's on ground?
hold on to that,
Air?
what supplies the force that's keeping that car into that circular path?
G force.
Sort of, I mean, it's basically, and Stefan's going to freak out, but it's the normal force. It's the normal force that's keeping it there, right? Inertia is trying to, the car is trying to go out of the circle, right? But the circle's there, and so what's pushing it in the center? The normal force. What has an effect on normal force? Does mass have an effect on normal force?
So you said normal person will do it up.
It does at the bottom, right?
Yeah, but now it says down.
It does at the bottom.
It's pushing down.
Is there a normal force right here? Pushing,
But then so that there's also gravity then.
there's also gravity, yeah.
Normal force now, then what cancels out the gravity?
It's a little confusing.
What forces are equal opposite to gravity plus normal force?
I was that
There- well, and that's a great question, Zach. That's why centrifugal force is a fictitious force. It's very real for the guy in the car. I mean, he's feeling that force.
real.
But we can't come up with something that would satisfy Newton. Newton says every action must have an equal and opposite reaction force. We can't come up with that other force in this instance.
Would there be like an extra normal force? Like 2 normal forces that are acting on?
No, there's no normal force up. There can't be, right? It's the opposite. It's the force that you feel because of inertia. Is it a real force?
So many stupid gray areas in physics. I hate it.
It's non-Newtonian. Yeah.
Let's do some.
Do some frame math.
Okay. The value of V min is called the critical velocity because if you're driving a car, it's pretty critical that you achieve that speed.
What about that bottom?
What about at the bottom? That's just a formula that tells you how fast you have to go to keep going in a circle. You can go as fast as you want.
To keep going in circles?
Keep going, yeah, but you won't fall off.
So that's our V
Could
curve.
you like go around like 6 times with that same velocity? If you had like a
Yeah.
half pipe type thing.
Yeah. Like if you had a double loop-de-loop,
Yeah, kind of like our
I bet she's going to try that next.
No, not a double loop. You just keep going in a circle. So go like up and then over.
Like a hamster wheel.
Oh, okay.
Yeah.
Yeah, I guess.
If a hamster can rip fast enough, there's like.
What you're saying is, could you go into like a pipe, and not a half pipe, but a real pipe?
Just keep going.
Just keep going. I don't see why
You
not.
can maintain that speed.
Yeah.
But you should maintain that.
And I mean, eventually you'd black out from the, I would think, because I mean, you could probably withstand the G-forces for the time being, right?
Also, there's like a certain length.
I would think so, wouldn't you? I mean,
Can we do it?
I don't know. I know we can Google it. Yeah, I don't know. Let me finish this up. Okay, so this value of V min is called the critical velocity. It depends only on the radius of the circle. And the acceleration of gravity, it does not depend on the mass of the object in motion. Only on a string. When you got something, a car, then, yeah, and friction and all that, yeah. A satellite that orbits the Earth, like the moon or any of the actual electronic telecommunication satellite, a satellite in orbit around a planet moves with the critical velocity for its radius of orbit. If it didn't move with the critical velocity, what would it do? Fly away. Or crash and burn. So it's a good thing that they move at exactly the right orbit. You could go slightly faster and you would just not be in a circle, you'd be more like an ellipse, which is really what is happening, right? But if you went any more faster, there would be a point where you'd launch, yeah.
So you guys went up into space like 3 satellites?
You can knock it off.
I guess, yeah. I mean, and every once in a while they have to do that, right? They have to do a little adjustment.
But you'd have to be going the same velocity stuff.
You would, yeah.
And then you gotta get the information.
You are going to see some satellite questions. Note that the radius of orbit for a satellite is equal to the radius of the Earth plus its altitude. I'm going to draw you a picture here. I don't know if it's, yeah, it's there. Good. Okay. You need this diagram. Okay. This is the Earth right here. This is the Earth. This is the radius of the Earth, RE. I think it's 6.4 times 10 to the 6 meters. One of these days I really got to go and do it. Mr. Bennett, do you happen to know the radius of the Earth? I do. It's 6.4 times 10 to the 6 meters.
What is 6.4?
Oh, yes. What is? The answer, the question.
But if it was on Jeopardy, it'd probably be.
That's true.
Probably what?
In feet, and then I wouldn't know it.
Do you watch TV at all and you see those repo game things? It's just like, how many
Wait, what?
feet is a football field? 3.
No, I don't.
What's that R?
So this is RE. The radius of the Earth is 6.4 times 10 to the 6. Then there's the altitude, right? The altitude is how high the satellite is above the surface of the Earth. And the total is my radius of orbit. That's the one you have to use when you're going V equals the square root of RG. Okay? You can't use altitude for radius because the radius is how far it is away from the center, which is the center of the Earth.
You add the altitude.
You have to add the altitude and that 6.4 number. Yeah.
Really, it's not that far.
Why does it have 2 arrows? That means it would just keep going and there's no distance.
So I'm just showing that's the distance. There's that. The RE is that distance.
Well, you have that R.
The altitude is that distance, and the radius of orbit is from there to there. R is the radius. This.
Over there.
The radius of orbit is the R important. Do you guys have the sample questions from yesterday?
No.
Can you find sample number 3, which is a vertical circle 1? 0.5 kilogram body moves in uniform circular motion. Now it says UCM. Is that really true? It's not really true, but it just means that we're going to assume that the V in the formulas is going to be an average.
Wait. UCM is.
You're right. Well, it's not entirely true. The formulas remain the same. The only thing is the V is the average between the min and the max. That's all. Okay? So we've got our vertical circular radius 1.5 meters. The period is 0.5 seconds. Find the speed of the body in its orbit. Okay? So once again, The velocity is the circumference divided by the time, so that's going to be 2 pi r over t. So we've got 2 pi. Yeah, the radius is 1.5, and my period is
Is that,
0.5. 2 times pi times 1.5. 2 pi r.
okay.
That's why I use the big R sometimes, because little r's are hard to make. And you should get 18.8 meters per second. All right. Now, to find the average centripetal force needed to maintain this motion, the average centripetal force. So we're talking here, Fc, mv squared over r.
What's MB?
mv squared over r is centripetal force. So 0.5. The velocity is my 18.8. Now, because that speed changes, that's why we get average force, right? Because it's average speed.
So if it doesn't use the average.
You could only find acceleration, right?
Over radius?
Yeah. Over radius. And that gives you 118 newtons. Now, is that 118 newtons constant? No. That's the average, right?
Well, I got 6.
I don't know.
No, it's squared. 117.8.
Round it up.
We can round up to.
I don't know.
Does that matter?
No, not to me. Okay, what's the string tension when the mass at the bottom? Now, this is the critical part here. So, is it going to be more at the bottom?
Yeah.
How much more? How much more? Okay, so what we're going to say here at the bottom is I'm going to say that the net force is enough to maintain UCM. Actually, it's just circular motion, I guess, right? The net force is enough to maintain UCM. Therefore, the net force is that average force that we just calculated is that 118. So the net force, the total of the tension in the string and gravity is 118. And now we just got to get our directions right. Okay, so at the bottom.
And that's because we're using an average?
Yeah.
Yep.
Yep. So at the bottom, basically what I'm saying is the string force plus the weight force has to be equal to 118. The string force plus the weight force has to equal 118. Now, this is going to be, now which way is the weight force at the bottom? Down. Minus 9.8. Which way is that net force? Which way is that 118 at the bottom? It's up, is it not? It's up. The net force has to be up so that it stays in. So this is positive 118, which means when I take my half of 9.8 minus 9.8 and take it to the other side, it becomes positive, right? This negative 9.8 is down. Weight force is down. Yeah. Which means that my string force is going to be 122.9. Okay, it's because the weight force is negative, it's down, it goes to the other side, it becomes positive. And we all know the tension has to be bigger. It's got to be more than 118 on the other side. Can you do the same steps at the top?
Yes.
What's different
Minus.
at the top? It's minus the weight force. But how do we make it all work out, Jordan, you think? Again, my string force plus my weight force has to equal 118, but which way is the net force at the top? It's down. My 118 is down. Right? It's negative 118.
I thought the top was FF, something minus.
And now when I go just let me finish here, and it'll make sense to you. And now when I go, is the wave force still down? You bet it is. It's minus 9.8. But now when it goes to the side, it still becomes positive, but now I'm adding it to that negative 118. And so my string tension is minus 113.1. Okay, negative because it's down. And numerically less than 118. Does that make sense?
Yes, but I don't like that. Tough is tough.
I think if you look at it long enough, I think it'll make some sense.
So, like, at the bottom it says FS2 minus.
Yeah, I sort of glossed over some directions there. This is what you need.
I guess because it's still a negative, so that's just plus.
All right, so whatever's left here, you can have to work. Yeah, we'll see if we can find one or two there. Tomorrow's work period, you can do horizontal and vertical circles now. Okay, and then starting on Friday, I think we need to go to banked and unbanked curves on the road, I think is the next topic, if I'm not mistaken.